Hi, welcome to the course, Raster Data and Analysis with QGIS. So this course is designed so that you don't have to have a lot of background in raster. I'm going to cover the basics of what raster data is and what you can do with it, and specifically how to work with it in the open source GIS QGIS. So my name is Kurt Menke, and I work with Septima. So I want to start by discussing different types of spatial phenomena. So we can broadly say in the data that we try to represent in a GIS, there's discrete phenomena and continuous. So discrete spatial phenomena are individually distinguishable. Data does not exist between observations. So an example of that might be tree locations, like these red points in the upper right. They're just single points in space. And then we have below that a road network, which would be another example of discrete spatial phenomena. Then we have continuous spatial phenomena. So this is where data does exist between observations. In other words, for elevation covers the entire landscape. Every part of the landscape has an elevation above sea level. Something like temperature or other climate variables would also be examples of that. So this is best represented with raster data. The vector data model is typically used to define discrete objects: fire hydrants, roads, ponds, parcel boundaries. And there's three basic types of vector data: points, lines, and polygons. And on this previous slide, when we were just talking about continuous spatial phenomena, I said that is best represented with raster data. But of course, you could also represent elevation as a vector data set, showing it as contours, contour lines. However, I think most people would agree that a raster data format is better for elevation than the vector equivalent. So then we have the raster data model, which is the focus of this course. So we have the landscape covered by an array of pixels or cells, and they have some kind of resolution, which we'll talk about. And it's possible to store any kind of feature, whether it be discrete or continuous, as either vector or raster. So here we have an example of some discrete features: points, lines, and polygons, stored also as rasters. So point features, if you were to rasterize them, every point would occupy one square cell. And there are many types of rasters. One example of a continuous raster would be an orthophoto or a satellite image. An example of a discrete raster would be land use or vegetation. So this is an example of a land use data set that we're going to be using in this course, where every pixel represents a specific kind of land use: agriculture or forest. Another example of a continuous raster is elevation, which we just talked about. So here's an elevation surface for the study area that we're going to be working in. Another example of a discrete raster would be rasterized roads, where we've taken a vector roads data set and converted it to raster, and we end up with this stair-stepped view of roads. So we won't be doing this in the course, but we will be going the other direction. We will be polygonizing or vectorizing a raster data set at the end of the course. So why use rasters? Well, on the pro side, they're better at storing specific types of data. For example, continuous data, such as elevation or temperature. And obviously, they're best suited for imagery. They're also very efficient for analysis and modeling, and often quite a bit faster than their vector data equivalent. On the con side, the coordinate precision is lower. This is because we have an array of cells and they occupy some amount of space, whereas a point, for example, takes up no space. It's just a single point. Another negative is that with higher precision comes a storage cost. We can decrease the cell size to get finer resolution rasters, but that increases the amount of disk space that will take up. The third one's in italics, cannot store multiple attributes, and this is not entirely true, which is why it's in italics. The typical raster will have one attribute, a numeric value. So that might be the elevation above sea level or a code for the land cover. But there is a plugin that now allows us to store raster attribute tables. So that's why it's been italicized here. Not historically possible, but it is now in QGIS. So I'll be talking about that near the end of the course. Next, I want to talk about raster resolution, which is the cell size of the raster. And it's given in ground units. So for example, a 5-meter resolution raster is every pixel is 5 meters on a side, and those pixels are square. So you can see that with smaller cell size, you have higher resolution, and larger cell size will be called lower resolution. And this will always be given in ground units. So the raster properties in QGIS look a little different than the properties for a vector layer. We're going to have the width and height in pixels. So the width of this is 3,172 pixels. We have a data type. We'll talk about what float 32 means in a minute. We have the driver or the file format. So this is a GeoTIFF is a particular raster format, just like a shapefile is a vector format. And then we have some statistics. So for the array of cells in this raster, they have a numeric value, and the maximum value is 39.4, the minimum is 2.3, and the mean is 14. So we always will have those kind of statistics. And then down at the bottom here, we have the pixel size. So in this example, it's just under 2 meters. We also have raster data types. So a raster can be signed or unsigned. If it's signed, that means that that raster data type can hold negative values. If it's unsigned, it will only store positive values. Then we have integer versus floating point. An integer raster can store whole numbers only, whereas a floating point raster can hold decimal places. And we get different combinations of these. So sometimes we'll have a signed integer or an unsigned integer, etc. This is a table showing the raster data types that QGIS can work with. So I'm not going to go through all these in tremendous detail, but the first one, byte, is an 8-bit raster and it's unsigned. So the fact that it's unsigned means it cannot contain negative values, only positive. 8-bit means it can store 256 values, so 0 to 255. Moving from 8-bit to 16-bit greatly increases the number of values we can store. This is an assigned integer, so it can store negative values. The unsigned integer, 16-bit, can store the same number of values, but here it's only positive. So it goes 0 to 65535, whereas here we have negative numbers that can be stored. And so on. This is a 32-bit integer. And then we'll get down here to float 32 and float 64. These are formats that allow you to hold decimal places. And typically these will also always be able to store negative values, so they are signed. We will be using usually some combination of float 32 and signed or unsigned integer in work. There are also these complex data types down here, which are a little beyond the scope of the course, but we can talk about those if people are curious during one of the question and answer sessions. So in this course, you're going to be conducting a potential vineyard analysis. You're going to identify potential sites for a vineyard for a small study area in Denmark. So you have 4 criteria that you have to work with. The land must be currently considered grassland or cropland, so that will come from a land use raster data set. The site must be on south-facing moderate slopes. That will come from elevation data, and you'll derive both slope and aspect from that elevation data so that you can determine which are moderate slopes and which are south-facing. The third one is that it should have one of several specific soil types. So there is a soils data set that's vector-based, has polygons, and you'll be determining suitable soils from that. And then finally, the site should be greater than or equal to 1.7 hectares. So there's a size consideration in the vineyard as well. So we're going to work with all 4 of these criteria to determine potential sites for a vineyard. This shows the course materials. You're going to have a course data folder, which will contain the data that you need for the course. The output folder will be empty. That's for you to store your model outputs as you move through the assignment. This lecture is in your materials as a PowerPoint. There's an instructions PDF that has detailed step-by-step instructions to follow through the entire course. And then there's going to be an assignment document that'll have an assignment to be done after the first class and one after the second class. So the data sources for the course, we have a land cover data set from the European Space Agency World Cover. This is a brand new data set just published in October of 2021, and it has 10-meter resolution. We'll be working with elevation from Denmark's height model that has 40-centimeter resolution. And then we have a soils polygon vector data set from QGIS that has produced at a scale of 1 to 25,000. So I want to talk a little bit about digital elevation models. We have one called a terrain model, and that is when the data represents terrain absent buildings, roads, trees, and things like that, just the surface of the soil. Then we have a digital surface model that does include the trees and buildings and roads and things like that, bridges. So we'll be working with a DTM. And sources for DEMs, there's quite a few. They come from elevation that's acquired in many ways. So you can acquire elevation from ground surveying or from GPS measurements. Once you have an array of points that have elevation associated with them, you can use interpolation tools to generate a raster from those. An old school way to do this was stereophotogrammetry, where you would take two aerial photographs, and if they overlapped by 60%, you could generate an elevation surface from those. People often created contour lines from those, and so another way of deriving a DEM is to digitize contour lines, and there's a method for creating a raster elevation surface from contour lines. A more recent technology is LiDAR or point clouds, which collect fantastic data that's very high resolution and can be used to produce elevation data. And so that's the source of the elevation data that we're going to be working with in the course. And then there's radar interferometry, which was used by the space shuttle in its missions, and the space shuttle missions resulted in 60-meter global elevation products that are available. So now I want to walk through the workflow, because there's quite a few steps in this workflow, and I think these flowcharts will help kind of keep you grounded as to where you are in the process at any given point. So we're going to start with the digital terrain model, and we're going to extract it to the study area. If you were to be working with a vector data set, you might use the word clip to clip it to a study area. With rasters, we extract those pixels from a given area into a new data set. We'll be doing the same with the land cover, which will also have to be reprojected. And these are in two different spatial resolutions. The DTM is at 40 centimeter. The land cover is at 2 meter. And we will be putting them both at 2 meter resolution, which is kind of a happy medium between those two resolutions and still has enough detail to be useful in a vineyards analysis. From there, we will align these rasters so that we get a DTM and a land cover raster that are perfectly aligned, so the pixels perfectly correspond to one another. And that will result in aligned copies of each of those rasters. From the aligned DTM, you're going to generate a slope data set and an aspect data set, which will show you which way the slope faces. We're then going to do 3 different reclassify operations, one on each of one of these. And that's because slope, for example, is a floating point data set that has literally millions of different values in it. And that's really too much data for us. We're really interested in aggregating those into categories that mean something to locating a vineyard. So that would mean that we're interested in slopes between 6 and 15%. So that would be we'll take all those values between 6 and 15% and aggregate them into one category. So we're going to basically be putting all of these into categories that mean something to vineyard analysis. And we're going to be, for aspect and slope, aggregating those into 4 classes, 4 being best for a vineyard and 1 being least ideal for a vineyard. For the land cover, you're going to reclassify that as 1s and 0s. 1s for suitable land cover and 0s for unsuitable land cover. So you'll end up with 3 data sets, and that will be half the course right there, is just doing the processing of the data to get it ready for analysis and getting these 3 data sets produced. We'll then, in the second session, go through and start with the slope and aspect reclassified data sets and bring them into this thing called the Raster calculator that lets us do Raster algebra to combine these. So we're going to add slope and aspect together and divide by 2 to get the mean slope and aspect. And remember that these will have values from 1 to 4, so this will as well. 4 will be most ideal for a vineyard and 1 least ideal. We'll then incorporate the land cover that's been reclassified, and this will be 1s and 0s. So we're going to use this in the raster calculator to multiply the mean slope and aspect by land cover, and any unsuitable classes with a value of 0 will result in 0 in the output, and the values of 1 will mean that they'll have the same value that they did in the mean slope and aspect. So we'll end up with a result that filters out the unsuitable land cover. We'll then use an operation to extract just the pixels that are greater than 3.5. So the maximum that they could be equal to is 4 because of our reclassification. And so we're going to say that greater than or equal to 3.5 is required for the vineyard site. And using this expression, it will output that final result where we'll have anything that is greater than or equal to 3.5 will have a value of 1. Otherwise, it'll have a value of 0. We're then going to convert that to a polygon data set, and then we can begin to incorporate one of the remaining criteria, soils. So this is a vector data set. You're going to select the suitable soils with an expression, and then you're going to dissolve that selected set to produce suitable soils. You're then going to incorporate suitable soils into the analysis by clipping the final result polygon by the suitable soils to generate raw potential vineyard sites. The last thing you need to do is incorporate size. So you'll calculate the hectares of each polygon, and you'll then filter that data set for those that are greater than or equal to 1.7 hectares to produce the final potential vineyards data set. So that's the end of the introductory video here. I look forward to meeting you in the class, and I hope you enjoy it. Thanks so much.